Hello, community. So great that you are back. Yeah, today we talk about a brand new research about small language models, and we will explore here a recurrent transformer architecture for some deep-seeking AI. So let's start. We can listen now in on the internal thoughts of an LLM. Wouldn't that be great? I mean, even more specifically, we can listen in on the latent chain-of-thought reasoning of an LLM, and that we can listen, understand, and optimize here. This would be the holy grail, no? And you know what? We can do this internally without any verbose text output. So this is really the internal calculation within the hidden layers of an LLM. And it promises to be faster, more efficient, less computational cost. General, because it doesn't depend if you insert your question in German, in French, in English, in, I don't know, whatever language you speak. The reasoning process is now independent of the natural language. It is not that if you ask a question in French, that you or that the LLM internally translates to English, reasons in English, and then translates back to French. This is all done internally in a vector space. And we have a model. Yes, absolutely. It's a depth-recurrent transformer that simply reuses its layers, its layer architecture at inference time multiple times. So we increase the computational depth per token, but we do not increase here the model size. So this sounds great. And now we want to know in the reasoning task, it's still unclear whether the improvement here, if we do here the reusement of layers, if this improvement stems from an iterative refinement, or, and this is the big question, we have the emergence of a structured chain of thought like reasoning that is now happening in our latent space, in our vector space. And here we have this beautiful publication from Meta and UC San Diego here from end of December 2024. And they already examined this and they said, hey, this is a promising approach to latent reasoning. We have recurrent methodologies, and you know RNNs, where our intermediate continuous hidden state are passed across now the reused multiple used layer structure to simulate a multi-step reasoning without emitting any language tokens. So they already were close here at the end of 2024. And then we had here the paper in February 2025 by Max Planck Institute for Intelligente Systeme, University of Maryland, and Lawrence Livermore National Laboratory. And they built now a model. And they built here Hugging 3.5 billion. This beautiful model. And they did it here for scaling up test time compute with latent reasoning with a recurrent depth approach. Now, you know, this is a beautiful model. It's not a new model, but this depth recurrent transformer, there is a little hint to it. No? It reuses its own layer during inference. Yes, beautiful. So let's say instead that you have now to go in with a 60-layer neural network architecture, you just have a 20-layer network and you just loop through a block of its layers 3 times. So this increases now the computational depth without increasing the parameter count. So is this working? And if you look here at the publication here by Max Planck Institute, you see their architecture is rather simple. You have here the prelude block, you have multiple recurrent blocks, and then you have a simple coder block. So let's have a look. The whole model is 100% a latent space calculating architecture because we have internal vector space mathematical operations that are happening without generating here text tokens. So we transform this back to our vocabulary token at each step. No, we stay within the latent space. And now the paper of today, the most important paper today, published 2nd of July 2025, is now by Brown University under the supervision of Harvard University. And they now come up and say, hey, we can do a latent space analysis. Now we have a deep dive. Now we listen in on the thoughts of an LLM. Absolutely fascinating. How they do this? They say easy. Extracting the hidden state vectors at each step of the recurrent process enables this. And we do have probing tools. If you want a microscope or a microphone that listens in and decodes here the meaning of these intermediate vectors in these artificial mathematical vector spaces that we build when we look here at the computation in between the hidden layers. Now, of course, you have here a GitHub repo. You see, README just updated an hour ago. Not a lot of traffic there, but it's an absolute fascinating paper. Let's have a deeper look. So, the entire process would be meaningless now if the computation wasn't happening here really in the internal transformer space, the, if you want, recurrent space, the latent space. So we are now trying to eavesdrop here on the silent internal conversation of the vectors that are here constituting here the layers. So the object of our study, if you want, is a vector trajectory, a multidimensional vector trajectory. And they analyze here the model's behavior, and we are not looking at words. We are just looking how do the vector change. And we are looking here for rank trajectories. And what is it? A rank trajectory is simply a plot of how the mathematical properties of a hidden high-dimensional state vector changes over time. Let's have a look a little bit more closer. Now you see it's absolutely the same idea here, even in the new publication from July 2nd. They say here, we have a human task. Now the human task is what is 3 times 2 minus 2. Now you know, at first we have to perform here the multiplication, 3 times 2, 6 minus 2 equals 4. So if we would have now an intelligent system, you would guess that somehow the 6 would emerge here as a vector representation, then maybe the 2 and maybe the result of a 4 somehow would be in this architecture, in this recurrent architecture. And again, as you see, we just have 2 prelude blocks, we have 4 recurrent modules, a transformer block, and then we have 2 coder modules, and great, no? And the result here, of course, should be then the final result 4. But we want now to pierce into the layer dynamics, and we want to see how the rank of the vectors, how the vectors itself change in this mathematical space. So we have 2 objects to do this. We have 2 microphones to listen in. The first is the logit lens and the coda lens. And you see, it's simply a normalization and a multiplication with an embedding vector, or we go here to the coda. I explain this in a minute. So the authors use here a simple recurrent process. No? They loop here through 4 recurrent units. So this means 16 times. And they analyze it as a giant 68-layer network. Because, as I told you, 2 prelude, 4 times 16 recurrent, and 2 coders. So those are all the blocks that we have. And this allows them to track how the representation now of these vectors evolve over the depth. Because now we have 68 layers. Of course, this depth is an artificial, reused, reiterated depth. Therefore, it is converted to time, if you want. And now to our 2, if you want, piercing microphones. These are the paper scientific microscopes for looking here inside the model. So let's explain them. It's very simple. The logit lens is a standard technique that you know. You just take a hidden state at any intermediate layer. You project it into the vocabulary space using here the model's final output layer and see what word the model is currently thinking of. Couldn't be easier. A coda lens, a little bit more complicated, but in general the same. No? We have dedicated coder blocks, C1, C2 at the end for the clean output generation here. And now the coda lens is a more faithful probing tool that passes an intermediate hidden state through these 2 powerful coder blocks, these 2 transformer blocks, instead of just the final linear layer. So this is a more, if you want, sophisticated methodology, but we would expect that this should show us in general here not a lot of divergence. If you're interested in the blocks, the prelude blocks here, 2 standard transformer block that just perform the initial processing of the input prompt. Then they go here with 4 recurrent modules, blocks, 4 transformer blocks, nothing special. Then the coder blocks, the final transformer blocks that take the result from the last recurrent step and, if you want, clean it here for a final coherent prediction, basic. But you notice something? We're talking here about a recurrent system. The recurrent mode here, or the module here, is a normal transformer block. It is not special in any internal architecture. And you know what? This recurrent is just because the way it is used. It is the model's computational path that loops back and runs repeatedly through it. So the recurrence here is an emergent property of the computational graph, not an intrinsic property of the block architecture, because we are here not an RNN, but we go here with a transformer block. So we do not have an LSTM or a gated recurrent unit here from an RNN in our recurrent neural network. We have it only as a property of the computational graph of multiple simple transformer blocks. Careful. Yeah, you can have now the state equation here describe the hidden state at each effective layer I, and the simplified version looks, and you know this now, so input we have the embedding, then we have the prelude, then we have the recurrent, and then we have the decoder, beautiful, and just tells us here, hey, the state Si is here the result of applying here the current block, the prelude, the recurrent, or the decoder to the previous state S at I-1. So, okay. So now what we find out, what the authors found out. Now have a look. Here we have both our microphones or our microscopes. Here's the logit lens and here's the decoder lens. And here we just have the block number, and you remember we have 68 blocks, so we go from 0 to 68 in both cases, and then the rank. And the rank of the final correct answer token is decoded from each intermediate layer, and the lower rank is better. Rank 1, for example, means it is the top prediction, and you would think that something would happen, eh? But instead, you have a smooth, steady improvement. This means decreasing here. If we run through all this, the trajectory shows wild periodic oscillation. It demonstrates really sharp discontinuities where the model seems confident in one step and then completely lost in another. So we go from a little bit knowing to perfect chaos, then a little bit knowing, perfect chaos. So lost, completely lost. So this graph here, if you look at this, it kind of screams to you, hey, the internal reasoning process is not smooth at all, or it's not stable at all from both our microscopes. This is not good because, yeah, you remember, logit lens, simply multiply with the final unembedded matrix W, and here you just go with the CUDA course. With the sorry, no, CUDA, not CUDA, with the coder modules, my goodness. So, crucial finding of this paper now, of today's paper, is that these two probes give wildly different results on the same hidden state. So, for example, at a particular layer, the logit lens might predict some givers like friendship. If you transform here the vector representation in the lingual representation, while the decoder lens predicts a number like 6. And this inconsistency casts here serious doubts on whether the hidden state has a single stable semantic meaning at all, which would be a prerequisite for any robust latent chain-of-thought development in the simplest case. But it is even worse than you might think. Because here we have now, again, logit lens and the decoder lens, a direct comparison of the rank trajectory for the intermediate answers. And you remember in our example, 3 times 2 should be 6. So 6 is the blue line here in both cases. Versus the final answer, the 4, this is the orange line. And what would you expect? You would expect if we have really a chain of thought, a linear sequence, step 1, then step 2, then step 3, that you would expect here the blue line to drop significantly first. So it finds here the first result, 3 times 2 equals 6. Followed here by a delayed drop in the orange line, because now we have here another operation, and 4, here's the final result. So these two lines should be separated. Yeah, as you can see, clearly shows the blue and orange line drop almost simultaneously in both our instruments where we have a look into the layer structure, the layer dynamic. Yeah? So there's no significant time delay, there's no phase separation between the model figuring out the intermediate steps and the final steps. So anything connected with a chain of thought is not really materializing here, if we look inside. So unfortunately, those are strong evidence that the model is not following a sequential step 1, step 2 reasoning process at all. We don't see it if we look inside the vector representation inside the dynamics. Here now, right next to it, we have here what happened if we increase the number of the recurrent step. And we have here explicitly here in the system message, we say, hey, we suppress here the chain of thought reasoning. So what happens if we go from a recurrent step of 4 to 8, 16, or 32 recurrent steps, or even 64, and you see, we go just on. And you see, you would expect, let's make it this way, if it would be anything like a chain of thought reasoning, if it would be anything like an improved reasoning, that the performance, if we run some benchmark test, it would go up, no? But look at it. At 4 recurrent step, we have an accuracy of 3. At 32 recurrent step, we have an accuracy of 5. At 256, we have an accuracy of 4.6. So increasing the number of the recurrent steps only gives here, in the simplest case, a marginal 1.8 percentage point accuracy boost, or even, it's not just a plateau, but it even has a light backward trend. So the performance is drastically lower than models that use an explicit text-based chain of thought, because you see, with the normal chain of thought, we are somewhere between 24-38%. So they say, okay, the authors now argue that this is the final nail in the coffin of the idea that simply a depth recurrence, a recurrent step, we go again and deeper and deeper and deeper over the same layers, is kind of a replacement for a chain of thought development. No. If we just run through the same layers again and again and again with time, and we think we're going deeper and deeper and deeper in the reasoning, it is not happening. It is not a replacement for chain of thought. So this is quite a negative result, I would say. Yeah? What are the main insights of the study? The latent reasoning here of this recurrent system is messy and absolutely inconsistent. When we decode here the intermediate and hidden state, the author found here sharp discontinuities. I showed you this. The layer might seem to be thinking of a number, while the very next layer in the recurrent loop outputs some gibberish, whatever. And the interpretation depends heavily on which layer you probed and which of the two lens you used, so no coherence in the system at all. And in addition, there's little evidence for step-by-step calculation. Huh? The authors tracked the model's confidence in the intermediate result, the 6, and the final result should be this one. And if a latent chain of thought were happening, the intermediate answer should become confident first, and then the final answer should become more and more confident, the AI. And they found no clear temporal separation of those. So, and in plus, they showed here the third effect, that if you go more depth, you increase the recurrent step. This is not at all a chain of thought. So this suggests that if we do now extra computation, either in the inference run or in the training here, whatever you add on computation is not being used for a structured multi-step reasoning at all. Wasted. So the result of this beautiful study by Brown and Harvard University, listening on the thought processes of a recurrent system of a depth-recurrent transformer. And the final result is, the authors tell us, we looked inside the latent space of this depth-recurrent model, and the operations that are happening are messy, inconsistent, do not resemble a structured step-by-step reasoning process. The latent computation seems to be more like a gradual refinement than anything that comes close to a logical chain. And you might say, but wait a minute. No, 2 days ago you showed us here a new AI model about hierarchical reasoning, and there we also used here a recurrent model. And you're absolutely right, if you are a subscriber of my channel. And at that time I told you here that the authors said our model achieves a spectacular performance on tasks that require multi-step reasoning. The operation happening in its latent space, so we are again operating here in the vector space, must be powerful, structured, and algorithmically effective. And in this video I showed you a result that was just amazing. And now we have nothing. So what is the difference? Have you spotted it already? Do you know it? Well, it's very easy. Remember that here in this particular case of hierarchical reasoning models, we were operating in transformer blocks that were encoder-only blocks, like using here bidirectional self-attention. So each token can look at all the other tokens in the sequence before and after itself. Great for understanding here the full context. Today, in the Hugging 3.5, in the Depth-Recurrent transformer, so both are recurrent systems, just to be clear. But today, we looked at the decoder-only blocks, like in GPT or Llama, that use your causal self-attention or mask self-attention, and each token can only look at itself and the token that came before it. So this is an autoregressive text generation that we know from GPT, and this is the first of the differences. We have not a transformer block, because a transformer block, if you have the encoder block, is totally different in its operation to the decoder block. Remember, this is BERT and this is GPT. So careful if you read transformer block. You have to specify which kind of it is it. And because we have bidirectional attention, these HRM encoder blocks are perfectly suited for all-at-once reasoning. Remember, we were doing here, what was it, Sudoku and chess. So we have complete configuration. With one view, we see here the complete chessboard and we have a complete understanding of the system. Here, on Hugging decoder blocks, we only have a left-to-right generation. We have an autoregressive token generation. Yeah? So, extremely limited. But I want to be clear, the Hugging paper does not invalidate here the HRM paper. Well, it's quite the opposite, no? It provides here a beautiful piece of context that makes here the result of HRM even more impressive. But if you go back to my video, you see they build a much more complicated architecture. Because the Hugging paper just shows that simple generic recurrence is not enough. There's nothing on spatial separation or temporal separation. This is just looping over transformer layers over and over again. You just get messy states and a weak performance if you just do the trivial, of course we do this thing. But where here on the other hand HRM succeed is it has special features. And remember 3 points I told you we have with a high and a low system operating within HRM, we have a hierarchical separation, plus we have a temporal separation. Like this slow, fast update, like this thinking 1 and thinking 2 for the humans. And then I specified here the deep supervision training strategy for this particular configuration. So it really pays if you are both on a recurrent system, but you really think about how the learning process should happen, how the reasoning process should happen, and how you build your training strategy. If you just take here a transformer block or transformer layers here, and you just have a recurrence here that you run over it without anything else, weak performance. But I think together, and this is why I show you this study today, together those two papers tell here a complete story, no? Because achieving here a powerful latent reasoning calculated in our mathematical vector space here after transformer blocks is not easy. And it requires here highly specialized, sophisticated architecture, like I've shown you in my HRM video, and not just a simple application of recurrence, like we saw on today's paper. So this Hugging paper provides you the baseline, if you want, that demonstrate what is not working and how special the achievements of HRM really are. Great! I hope you enjoyed it. If you want to see more videos like this, why not subscribe, and I'll see you in my next one.